Dear TYBSc friends, in earlier two sessions or this introduction to laser, we have seen very fundamental concepts used in classical mechanics, that is wave theory, as well as in quantum mechanics, that is quantum theory of light. And also we have discussed the concept of this thermal equilibrium, that is called as Boltzmann equilibrium or Boltzmann equation. Using this Boltzmann equation, how this thermal equilibrium what this thermal equilibrium tells us, that predicted that at ordinary temperature, the most of the atoms are found in the ground state or in the lower energy state rather than these higher energy states. And in that concern, there is one more very interesting prediction was done by Albert Einstein in 1917, where he showed that there is absorption of energy, and therefore the atom can go from lower energy state to higher energy state, excited state like E1 and E2. In after some time, that atom in this E2 gets de-excited and comes down to the lower state E1, and in that case it gets rid of some energy, or it gives out the amount of energy it has absorbed, and this is what called as the spontaneous fission, spontaneous emission. Along with that, Einstein proposed that there may be third more method of this emission is possible, second method of emission, that is called as induced or stimulated emission. So he had given the reasoning. While this absorption occurs because of this incident of this photon, this is the photon light or light field, we say, these photons are accepted and therefore this process occurring. And at the same time, if some photon comes again and this photon compels this atom to come down, this type of emission is called as either induced emission or it is called as stimulated emission. And this stimulated emission is one of the very fundamental process in case of this understanding of this laser working. So we are going to discuss all these things one by one. Before that, we are going to see certain Einstein constant or Einstein coefficients for these three different types of processes. What we have seen, that is called as the absorption, first one. Second is the emission, spontaneous emission, and third one is the stimulated emission. So what happens, how to go for this particular constants or coefficients, that is the point of discussion for this particular session now. So as usual, consider there are two cases, two energy states denoted by E1 and E2. And in E1, the population of E1 is N1. So this is as usual. First state is E1 and population here is given to be N1. Second state is E2 and population in this case is given to be N2. And delta E is the difference between this E2 minus E1 as usual. So this is the same case we are using here. So let the atom be in thermal equilibrium. So whenever they are in thermal equilibrium means whatever number of transitions taking this place from this side to this side, same number of transitions are taking from this side to this side, and this particular the higher energy state to lower energy state. And this in the equilibrium condition, the number of atomic transitions upward must be equal to the number of downward transitions. Thus no net photons are generated nor that is lost. So no photons are absorbed or no photons or extra photons are generated. So whatever number of photons in the system is always found to be constant there, because we are at thermal equilibrium. And however, when the atoms are subjected to an external light or frequency of nu, then the following three processes occur, and that is what we are going to see one by one. So in detail, we are going to see first process, that is called as absorption. Okay, so let's see in the detail what this absorption means, what happens here, occurs in this particular case, how to go for this particular situation, wherein we have to go for calculation of this Einstein constant and all these things. So an atom residing in the energy level, lower energy level E1, may absorb this incident photon and jump to the excited state E2. Okay, that is that diagram we are going to draw here. This transition is known as induced or the stimulated absorption or simply absorption, and corresponding to each absorption transition there is loss of photon from the photon field, one photon from the photon field, and one atom gets added to this population at the excited state. So loss of photon in the photon field or the light which is we are eliminating that particular surface source or the material, and one of these atom goes in the excited states, and this particular process may be indicated or shown like this. So this A is the initial atom, so it absorbs energy h nu, and goes in the excited state as goes and this A star. So A star is shown to be this excited state, A is the normal state, and Hd is the amount of energy that is incident here. So we can draw this particular process again diagrammatically, same diagram we have repeated earlier too. So this is my E1, this is E2, and here this energy increases in this direction. The photon is incident here, this direction, and thereby this electron here, that is, or the atom here in this particular state, this photon energy is exactly given to be h nu is equal to simply E2 minus E1. So whatever difference between these two, this particular difference is exactly equal to the photon radiation that is coming in. And now because of that, after this particular process is completed, you'll find that situation is a bit different. So this is now E1 and this is E2. This time this atom will be found in this state. So this is after, so this is before this type of absorption occur, this is the after this absorption is occur. And therefore if I go for materially showing all this what is happening there, in this case there are certain radiations, these radiations are being absorbed by some atom A here. Then there are some possibility that some radiations may reach to some another stage there. There is another possibility also, there can some more radiations can go to this another third possibility. So every time this incident photon is being absorbed and this concerned atom goes from low energy state to high energy state, and this particular process is called as the stimulated absorption. So this is stimulated absorption or simple absorption, stimulated absorption. And we have shown here this particular reaction can be shown. A is the normal atom if it is absorbing this energy h nu given by this incident photon, and thereby it goes into this excited state as shown in this A star. So A star is this excited states. Now we are going to go for a simple calculations in the following way. The number of atoms per unit volume, the number of atoms per unit volume. Now look at this number. This is what the basic definitions we are using here to go for these type of constants. That makes upward transition. That makes upward transition from E1 to E2, or lower level to upper level or higher level, per second. Per second. See the definition: number of atoms per unit volume that makes upward transition from E1 to E2 per second is called rate of absorption. Is called or is defined as a rate of absorption per unit volume. Number of atoms per unit volume that makes upward transition from E1 to E2 per second is called the rate of the absorption transition. So this is one transition, that is the absorption transition is occurring in this case, and mathematically it is represented as R absorption. Okay, I am using this word ABS for absorption. This rate of absorption is minus dN1 divided by dt, because N1 is the number of atoms in the ground state, that is the population of the ground state atoms. Okay, and where this minus dN1 upon dt, okay, this is a negative here, stands for rate of decrease of the population. This is related to rate of decrease of population of N1, and that's why negative symbol is given there, population of N1. So this minus dN1 upon dt represents the rate of decrease of population of the lower energy level, that is E1. And now the another way we can this same rate of whatever absorption, that means whatever decrease in the population of level 1, that will be an increase in the population of level 2, and thereby the same R absorption rate, another expression I can write in this form. So this rate also can be represented as because whatever number of atoms leaving this E1 state and moving to this E2 state. So this also can be represented with that particular factor again, represented as increase in terms of increase in population of E2, that is in terms of N2. So N2 is related to that, and therefore I can write another equation here is R absorption is equal to, this time it is dN2 upon dt, because of this process number of atoms or the population of E2 is going to be increased, and that's why this is going to be positive, and that's what I have written this equation. Therefore both of these equations can be seen to be same, so I can write R absorption is equal to either dN1 upon dt, or this also can be written as dN2 upon dt. So both of these rates or both these interactions of this particular rates gives me same process. That is what we have written here. So the number of absorptions transitions occurring in the material at any instant will be proportional to the population of the lower level. That means how many number of atoms are in the lower level, and the number of photons per unit volume in the incident beam. So for a given sample or given material, this rate of absorption or this R absorption will be dependent upon the, this is what we said, it's a dependent upon the population or in the state E1 or the first ground state, as well as it will be proportional to the number of photons incident. So if it is number is very small, then this rate of absorption will be small. If this number is larger, then this number would be larger, and along with that how many number of atoms they are found in the ground state or the E1 state. These are the two factors over which it particular thing depends. Okay, and therefore this total rate, therefore the rate, these are taking these two factors in consideration, we can write the rate of absorption of can be expressed, the rate of absorption can be expressed conveniently, Why conveniently? Because we are taking both the factors, that is this the incident photon density, that is the incident photons, as well as we are discussing or we are thinking or considering the population N1 too. So it depends upon N1 as well as it depends upon the intensity of the incident photon or the number of incident photon, and therefore another very good relation for this R absorption can be written as, now this time I am writing this is proportional to this rho nu, that is the photon field or the photon intensity, photon energy. It is proportional to this N1, that is the number of the population of this first energy state E1, and I am writing there is some this proportionality equality sign can be written, and this constant I am writing for the first time, that is B12. So this is a transition going from energy state E1 to energy state E2, and this rate of absorption in this case is equal to this coefficient, transition coefficient B12 into rho nu, that is the photon intensity or the number of photons incident or elimination, and this N1 is the population of this state E1. So B12 rho nu into N1, that is one expression where, so this is first coefficient we have written here, B12. Okay, let's see what this, it's a constant of proportionality. This is constant of proportionality. This is the constant of proportionality. Then this rho nu, this is said to be the energy density of incident light. Energy density of incident light, or that is also it is going to be number of photons per unit volume per unit area, whatever we can use that. That's why it's a number density or energy density of the incident light, and therefore this first P12. Now this is one very symbol we have to go for this. This is called as Einstein coefficient for induced absorption. So this is Einstein's coefficient for induced absorption. Remember this, it will be, there will be some questions that will be based upon this B12, and that indicates what it represents. it represents indicates the probability of induced transition from level 1 to level 2. So that is what we are getting from level 1 to level 2. This type of induced transition or induced absorption is represented by this particular coefficient that is given by B12. So B12 is for absorption or induced absorption. Okay, this is what we have to remember all the time. It will be required here. At thermal equilibrium, the population of the lower energy state, that is much larger than the higher energy state, because we are in thermal equilibrium. Therefore, as light propagates through the medium, it gets absorbed, and more number of atoms from ground state goes into the excited state, and that's what this particular entire transition. We have discussed this transition from lower energy state to higher energy state by absorbing these incident radiations or incident photons, and therefore B12 is the expression, or B12 is the term that defines your first coefficient, that is called as Einstein coefficient for induced absorption. Now for emission, we are using these coefficients A12 or A21 like that. Now we are going to discuss the second process, and therefore it is process number 2 or B, that is spontaneous emission. Spontaneous, SPONTENEOUS, TANEOUS, spontaneous emission. Now, as usual, we have already seen this. Spontaneous emission is where this particular atom, once it is excited in the excited state E2, this doesn't remain for a longer time there. This is E2 there, and without any external agency, this atom comes down to this ground state. This emission is called as, this is associated with the emission of photon of energy, which is given by h nu is equal to E2 minus E1, and this is a spontaneous process as it is not being supported by anyone else. So this is the spontaneous emission, and this process in which excited atom emits photon all by itself, okay, and without any external inputs, and that's why this is called as spontaneous emission. It's just spontaneous, it is by on its own. We do not do anything in this particular case, and therefore from the material, if I draw this material here, after some time all these atoms are there. These are the atoms, these are the excited states. This is A start, A states, etc. All this de-excite, and that gives out you radiation or energy out of this. So this is the spontaneous emission, and therefore here this reaction what we have written earlier, I can write this reaction here. It is A star goes into A, it's a normal state, and plus it introduces energy, this given by h nu, that is the amount of energy emitted in this process, that is called as spontaneous emission, is given by h nu. The atom was in excited state, it goes into de-excited or normal state, ground state, and it emits energy of amount of exactly equal to E2 minus E1, and that is again equal to H2, and therefore the rate of spontaneous emission, spontaneous emission. Earlier we have seen this rate of spontaneous absorption. We have seen this is proportional to the number of incident photons, that is photon density, as well as radiation density or photon density, as well as it is proportional to the number of atoms or the population of the state E1, that is N1. So there are two factors were there. Here it is not that. Here, since there is no one is responsible for carrying out this type of transition, only the atoms present in the excited state or the population of N2, that is only responsible factor for this type of rate of spontaneous emission, and therefore this rate is given by, okay, now another symbol is used here, RSP, spontaneous emission, and this is found to be minus dN2 upon dt. Since here minus negative sign here, again this N2, number of population of N2 or E2 level is going to be decreased because of this type of phenomenon of spontaneous emission. And further this can be written as, okay, it's very simply, it is written as N2, population of the level E2, and divided by, there is some time which is called as the TSP. Now this tau SP or TSP is called as the lifetime of that particular state or the E2 state, wherein it, that is the excited state, wherein this particular atom remains in that particular state. So this particular rate of spontaneous emission is directly proportional to n2, as well as it is inversely proportional to the time rate at which it is that particular atom remains in that state. If this rate is very small, this RSP is going to be very large. So all the atoms, whatever in the excited state, they are going to go into this ground state or lower state very immediately if this TSP is larger. If this tau SP is larger, that is greater, then the rate will be affected by that, and therefore I have written this expression RSP is equal to N2 upon tau SP. So this time comes in the denominator because that decides the rate. If this tau SP is bigger, large time that atom spends in that particular second state or excited state, then this RSP will be smaller. As well as when this tau SP is very small, that means for a very small time that particular atom remains in this excited state, then RSP will be larger, as well as how many number of atoms there are in the excited state, that is the population of N2. So these two factors decide this particular formula, that is RSP. Okay, and here therefore there in these terms of this Einstein constant, we can write this particular relation as number of photons generated will be proportional to the population of the excited level only, and may be expressed as, and therefore this relationship also can be written as RSP is equal to, now this constant I am writing here to be, this is A21 multiplied by N2. Again, N2 is the population of this level E2, and this A21 is the constant which decides what is the rate of SP. So this is one practical relation, and this is another theoretical relation one can write in terms of this type of coefficient given to be A21. Why A21? We are coming from state 2 to state 1, spontaneous emission, and therefore this coefficient is written to be A21, and therefore this is called as A21 is called as this A21 is called as Einstein coefficient. Einstein coefficient for spontaneous emission. Spontaneous emission. SPONTANEOUS, spontaneous emission. Okay, and from these both of these relations I can find out here, or I can write this is E21 into N2 is equal to N2 upon this tau SP, and that indicates this coefficient A21 or Einstein coefficient for this spontaneous emission is reciprocal of its lifetime of this atom in the excited state. That's what we have written. A21 is equal to 1 upon T tau SP. Thus the reciprocal of the coefficient of A21 is the time for the spontaneous transition, that is tau SP, and that represents the lifetime of spontaneous emission also. So it is the average time for which the excited atom would remain in the upper level before undergoing a spontaneous emission. That means for how much time that atom remains in this excited state, that average time is going to be tau SP, and this particular time decides the rate of, that is the constant in this particular of the equation of rate of this spontaneous emission. So this rate is directly proportional to N2, and it is equal to A21 times N2. But here this rate is also inversely proportional to this tau SP, and this particular constant is nothing but this second constant, that Einstein's second constant A21 is the constant for this type of spontaneous emission. So remember, P12 this is for absorption, and A21 this is for emission. So emission and absorption, accordingly we use these particular constants. And remember here in case of this type of spontaneous emission, no way these atoms from state 1 to state 2 can go there. That means when I go for this type of coefficient, when I go for this coefficient A12 is the spontaneous emission from level 1 to level 2. This is never going to be possible because automatically or on its own atom will never go from state 1 to state 2. This spontaneously it will never happen. Therefore this coefficient A21 is there, which is given by 1 upon tau SP, or this is given also by another relation too. But this A12 is not possible because this shows you that this energy or the transition from spontaneous emission, okay, so that tells you spontaneous emission from E1 to E2 is never possible, and in that case never possible. Therefore Einstein coefficient for transition from spontaneous transition from E1 to E2 is not there. It is almost equal to 0, is always equal to 0. So this A21 is non-zero, but A12 is taken to be 0 because of this particular possibility. And in that concern, we are going to see there are 3 or 4 important parameters or the important features. Okay, so what these features are, we'll discuss one by one. So important features. And these features are very important for us to understand. Once we understand this, then we can study the same features, similar type of features of this simulated emission too. So first feature is the process is spontaneous emission is amenable for control from outside. So this is spontaneous. That means out of control of anything else. No one can do anything in that particular case. So it is amenable for control from outside. So no control or this process can be done from outside. Then second, as it is statistical, it is the probabilistic in nature. Probabilistic, SPIC, probabilistic in nature, statistical process. We cannot predict that a particular atom will undergo this type of decay or will go into the lower state. We can only talk in terms of percentage or chances, that there is a chance, 100% chance, 10% chance, 20% chance that a particular atom will go from excited state to de-excited state, or from excited state to normal state. So that's why this particular phenomenon of spontaneous emission is this probabilistic in nature. Third important parameter here, that is this this particular case is a direction of propagation and initial phases of the and plane of polarization of each photon will be random. So that's what it's a random phenomenon. Random means once this particular process has started, radiations can come out here, it can come out here, it can come out here, and their polarizations and maybe polarizations of these waves may be in different directions, intensities may be different in different directions, and that's why, and there is not guaranteed every time a single wavelength h nu or single wavelength that lambda will be emitted. In this case, there is sometimes there is a case that is called as line broadening. So line broadening, and this particular process of broadening is the process that is what it is not monochromatic, chromatic. It is not a monochromatic. So these are the important features. Because of this line broadening, a single wavelength is not possible, a multiple wavelengths are possible. Then there can be several different types of directions of polarizations, as well as several different types of directions of radiations emitted, and that's why this entire process is said to be some random process. It's a probabilistic, it is spontaneous, it is random, and light spread in all directions. Because of this directionality is there is no lack of directionality. Lack of directionality, and that's why light spreads in all directions. And remember, exactly these are not the properties of laser. Laser light is supposed to have properties exactly opposite to what we have discussed here. So it is not spontaneous, it is stimulated, it is to be controlled by someone else. It is now not probabilistic. Here I can specifically mention that this particular number of atoms will go in the process of this decay. Now this time it is not going to be random, because whatever light emitted in this case will be a coherent. All radiations will be in phase, they will have single wavelength, that's why monochromatic. and now they have a good directionality. That means there is no directionality will be a high directionality with there, which was not there in the spontaneous emissions what we have seen here. Okay, and therefore this light intensity goes on decreasing rapidly. That means in this process, because of this, all this in all different directions, this light radiations can go out of because of this spontaneous emission, and therefore light intensity goes on decreasing rapidly. Okay, so fifth feature of this, light intensity decreases. Intensity decreases rapidly. Decreases rapidly. Okay, so just remember these particular types of characteristics. Maybe sometimes in examination you will be asked all these cases here. So here I can go for another important thing here, and the light is incoherent too. So 6 is the incoherent. Incoherent, that means the phases. So one is having this phase, okay, another is having this type of phase, third is having this type of phase. So this is a case of incoherence. So that is one possibility in this case. Okay, and therefore this total energy here, I can go for this intensity, the net intensity due to superposition of all such incoherent waves. Okay, so net intensity due to all incoherent waves proportional to the number of radiating atoms, and this is given by capital I total. I total is equal to N is the number of atoms and I is the intensity of radiation emitted by each atom. So that is N into I. That gives you intensity of light emitted by one atom. Okay? Intensity by one atom. Intensity of light, or that is radiated by one atom. Intensity of light by one atom or single atom, and this N is the total number of atoms present in this case. Now the process is emission dominates in the conventional light sources. So in conventional light sources, whatever light we get from the bulb or sun or any other sources, here in this process, everywhere, every time this process of spontaneous emission takes place, and that's why the conventional light is the source of the conventional light is this spontaneous emission. Okay, so source of conventional lights. Conventional means all lights we use for illumination purposes. Source of conventional lights is spontaneous emission. It is a spontaneous emission is the process that is the source of all the conventional lights what we see around us. And if only there are two processes, as we said, if only two processes are there, that is spontaneous induced absorption and spontaneous emission, then namely under the equilibrium condition, we must have this rate of atoms that are going from state 1 to state 2. This is absorption must be equal to number of atoms that are going from state 2 to state 1, that is the emission. So absorption and emission must be equal to same. Earlier we have written equation for this dN2 upon dt, as well as we have written this equation for dN2 upon dt, that these earlier rates, this is the rate of absorption, this is the rate of emission and spontaneous emission, and therefore using earlier relations there, we can write very simple relation B12 into rho nu, this is the photon intensity, into population of E1 state, that is N1, and here in this case it is given to be A21 into N2, that is the population of state E2, and this is A21 is the Einstein coefficient for spontaneous emission. B12 is the Einstein coefficient for this induced absorption, and therefore from that I can write relationship for this rho nu is equal to, very simple relation, rho nu is equal to A21 divided by B12. Try to understand this relationship, and it is multiplied by N2 upon N1. Earlier we have seen this N2 upon N1 is one relation that is given by, that is what is relative population of the state 2 to state 1, and we have seen that earlier in earlier session it is given by e raised to minus h nu upon kt. So therefore this rho nu is given by this coefficient E21 upon B12 into e raised to minus E upon kt, or h nu upon this is kt, h nu upon kt. So I can write this particular relations. Remember, same is the relation that one can go for Planck's radiation law, and in the Planck's radiation law we also get similar type of relationship for this e raised to h nu upon kt. And this factor here, E21 upon B12, whatever written here, that may be something different. Actually, we are not going to go for discussing this particular fact, but this type of radiation was confirmed by Planck in his black body radiation. So black body radiation, similar expression you might have come across. So this is the black body radiations. Actually, we are not going to concern about this more in this case, and therefore what important things in this case what we have discussed here, from both of these equations we understand that probability of the spontaneous transition is determined by only the population of the higher energy level, that is E2, whereas the probability of the absorption transition is determined by two factors. Earlier we have discussed this. One is the population at the lower energy state, that is E1, that is what we have taken proportional to N1, and the second is the density of the light energy, or that is the illumination amount of radiation that are incident here, that decides the absorption as well as the number of atoms which are found in the ground state or the lower energy state. These are the two factors, and that's how absorption and emission are different. So if absorption and spontaneous emission were the only processes operative, obviously the number of atoms absorbing radiation per second would be more than the number of atoms emitting light per second. Eventually we may end up with a non-equilibrium condition where almost all atoms are excited. So once these particular two processes are there, this would have happened, this more number of atoms would be found. That means if I go on eliminating this particular surface and a particular substance, now in that case these atoms are going, each and every atom is absorbing this radiation and reaching toward this higher energy state, and this type of non-equilibrium may be existed because of this particular type of situation. So eventually we may end up with non-equilibrium condition where almost all the atoms are excited, but this is not observed in practice. It means that the equilibrium is maintained every time for any of the substances in order to account for the existence of the state of equilibrium between light and matter. That means always there has to be like equilibrium between light and matter, or equilibrium in the state, and therefore every time the whatever number of atoms going from state 1 to state 2, by absorption same number of atoms will be coming down from state 2 to state 1, that is by the spontaneous type of emission, and then this equilibrium will be there. Okay, and Einstein concluded on that if a photon can, on the basis of this he concluded that if a photon can cause induced absorption, why not a photon can cause this induced emission, or that is called as stimulated emission. That's what this concept here we are going to discuss in the next discussion here. That is what we are going to discuss here. So Einstein concluded from this discussion that if a photon can stimulate an atom to move from lower energy state E1 to higher energy state E2 by means of absorption, then a photon should also be able to stimulate an atom from same upper state E2 to the lower energy state, that is E1, and this alternative mechanism of photon emission depends on the photon density present and is called as the stimulated emission. So this concept of controlled emission or stimulated emission, this is what for the first time it was given. It was thought by Einstein, and then people started working over this type of phenomenon, and then later on this phenomenon was used to generate this type of laser. So the generation of laser is possible. Now what is this situation scheme here? We have to raise all the atoms, as many as number of atoms from lower state to the higher state, and we are not allowed them to come down spontaneously. If they come down spontaneously, then there will be again an ordinary radiations will be emitted by that particular material. Somehow these atoms are to be allowed, or they are compelled to remain in some stable state as compared to this unstable state, that is called as metastable state. And once this is done, then immediately with some incident radiation, all the atoms that are at once, all these atoms are supposed to come from this excited state to de-excited state or lower state, and in that process simultaneously a large number of photons will be emitted, and that is the basic concept which is used in the generation of this type of laser light. And in that concern, we are going to discuss third important type of transition, that is called as stimulated emission, and that is what this is the most important for all of us. So this is stimulated emission. And once we understood this concept of stimulated emission, then it is very easy to understand this phenomenon of the particular case. So here also I can draw the similar diagrams which we have drawn earlier several times. This is my E1, this is E2, and here incident photon is coming in. This is the energy that we have shown earlier. This incident photon is coming here of the energy h nu is equal to E2 minus E1. Thereby this atom is gone from, this has absorbed this energy and it has reached here. This is the absorption has occurred, and now I am allowing this atom to come down from this E2 to E1 by the process of another incident photon. Another I am talking incident photon is there, and this photon again exactly having H2 is equal to H nu is equal to E2 minus E1, and this time because of this particular atom comes down to this ground state or this state here, which is called as the first energy state E1. And in that case, because of this incident photon or the triggered photon or this additional photon, one more photon is, two photons will be given out here. This is one is original, which is coming here, and second is radiated by this is what. So I am getting two photons of same energy, same frequency, same parameters, same all phase, provided this particular photon comes in, and that causes this emission of this causes this atom to come down from excited state to de-excited state, and this particular phenomenon is called as stimulated emission. So thereby I can draw another very simple diagram which we have drawn earlier to here. So this is my incident photon. Here this is the excited atom A star, and this gives rise to an incident photon, as well as this is the de-excitation energetic photon. There is one more radiation which is having some more depth. Here also this atom A star or excited atom, this also gives rise to a photon here, and another photon is exactly similar to this. So both of these photons are there. Another radiations can be shown here well deep inside there. This is one more atom that is in the excited state. This also gives out the radiations which are exactly in phase and same here, and that is how we are getting, this is what a laser light. So this is the laser radiations. Here we are going to discuss more about this later on, but this phenomenon tells you an atom in the excited state need not wait for the spontaneous emission to occur. If a photon with absorbing energy h nu is equal to E2 minus E1 interacts with such an atom, such an excited atom, then it can trigger the atom to undergo the transition to the lower level and to emit another photon as shown in this particular diagram. And this type of emission, okay, the process of emission by the process of emission of photons, okay, so we'll write in short, the process of emission of photon, emission of photon by an excited photon, excited by an excited atom. Process of emission of photon by an excited atom through, this time it is through a forced transition. This is forced one. Through a forced transition occurring under the influence of, occurring under the influence of external agent or trigger. External agent or trigger is called induced, is called Okay, this is what called as either induced emission, or this is also called as the, as we have said, this is also called as induced emission, or this is called as stimulated emission. Okay, is called induced. Okay? This is not natural. This is carried out by some external agency or with the help of some external agency. That is the photon again of the same energy, that is h nu. Induced emission, or this is also called as the stimulated emission. It's also called as stimulated emission. So induced or stimulated emission is the same, and therefore I am showing this process as, okay, see the relationship. Earlier we have seen this one relationship is A absorbs h nu, and therefore it goes to A star. This is excited. In this spontaneous emission, A star gets de-excited and gives me A and h nu again. This was the second reaction. Here we are having this A star, and this time this another energy h nu is again incident, or there is interaction between this photon and this excited atom, and that gives me A here and plus h nu here, and earlier one h nu that has absorbed there, so it is twice h nu. So this process h A star plus h nu, that gives you A plus twice h nu. This is the process, or this is the equation required for this type of spontaneous emission, this induced emission, or this type of stimulated emission. And therefore the rate of, on the same lines we can go here, the rate for, or rate of stimulated emission of photons. Stimulated emission of photon. Rate of stimulated emission of photon, if it is written here, this can be written as, see, R. I'm writing this to be RST, stimulated emission. SP means spontaneous emissions, ST means stimulated emission, and this time I'm using, this is, since it is in absorption as well as this is what B21. Okay, I'm writing this to be B21. This is rho nu and multiplied by N2. So since this is, even though it is an emission, I'm using this coefficient B type of coefficient, or B21, because in this case the atom is coming from excited state to de-excited. Force journey is there. That means this atom is forced to go from state energy state 2 to energy state 1 with the help of this incident photon, that is rho nu, intensity of that, and N2 is the population of this particular state, E2 state, and that's why this relation RS2 is equal to B21 into rho nu multiplied by this N2, and here this coefficient B21, this is called as the Einstein coefficient for stimulated emission. Einstein coefficient for stimulated emission. Is called as Einstein coefficient for stimulated emission. Okay, so see here we have seen this three. First we have gone for, in first case we have gone this first relation, that is B12. This is for absorption. Then we have gone for A21. This is for spontaneous emission, and now this time we have gone for B21. This is the Einstein coefficient for this stimulated or forced stimulated emission. Okay, so try to understand, these are the three processes what we have learned here: induced, absorption, spontaneous emission, and the stimulated emission. So these three processes that are important process, and these are the three constants that we are supposed to be seeing here. And now there are certain features of this particular process that will be see here in the next session. So that particular features we will see in the next session. Therein we are going to look, once we understand this type of phenomenon of this stimulated emission, there are certain possibilities, certain features of this, and in that case we are going to study these features that leads us to the amplification. So why phenomenon of amplification occurs here in such type of stimulated emission, as well as why intensity is more, it is possible, then why this type of the directionality is there, why there is a coherence. All these concepts, basic concepts associated with this laser that can be understood from this discussion of the features when we go for these features of this particular case. At the same time, we have to go for another types of relations which are called as Einstein's relation, and then we will finish this chapter 1 there after this session number 4 or this chapter 1. So till then, have a good work, good time, and we'll be there in the session 4 once again after some time. Thank you.